find the general solution for this differential equation, y double prime plus 2y prime plus y equal to cosine squared of x. Now, there are two ways of solving this problem. You might either use variation of parameters or undetermined coefficients. Remember that I can rewrite cosine squared of x as 1/2 plus 1/2 cosine of 2x. So rewriting this one, I have y double prime plus 2y prime plus y equal to 1/2 plus 1/2 cosine of 2x. Now, why am I rewriting this one? So that I can use the undetermined coefficients, since undetermined coefficients only can only be used for functions of cosines and sines of having first degree here. So the first thing we're going to do is to solve the homogeneous portion of this. The homogeneous portion of this one is just to set this into 0. So in order to solve for your homogeneous part, you are going to replace y by m and its order by the exponent of your m. So for this case, I can rewrite this as m squared, since this is of degree 2, plus 2m plus, since the degree of m here is 0, so I can just write this as 1. And this is equal to 0. Now, solving for m, I can factor this as m plus 1 squared equal to 0. So I have values of m. m1 is just equal to m2, which is equals to -1. So we have here that if your solution has the same value for your m1 and m2, then this takes the form, that takes the form c1 e to the m1 x plus c2x e to the m2x, where our m1 and m2 are equal. So our solution yc for this homogeneous equation is just equal to c1 e to the negative x plus c2x e to the negative of x. Now recall that the complete solution of our differential equation is composed of y, which is equals to yc plus yp, where this yp corresponds to the solution for your homogeneous part and yp is the solution, is a particular solution. So the form of your yp here depends on the form of your non-homogeneous part, which is this one. So observe that for our non-homogeneous part, this is composed of a constant plus another constant times a cosine function. Now, according to our differential equation book, if we have this a form like a constant, say for example a times a cosine function, for example u, we can the form of our yp will then a cosine of u plus b sine of u. So even if this will be c sine of u, this will still be a cosine of u plus b sine of u. So that's the form. So for this case, the form of for our yp is just equal to, since this is a constant, so let's label that constant as a plus another constant b cosine, here our u is 2x plus c sine of 2x. Now, don't use a here, since these three constants does not have equal values. They have different values. Now, we have more than 20 alphabets there, so just make full use of them. So the next thing we're going to do is we will get the first and the second derivative of our particular solution, and after that we are going to substitute the first and second derivatives here and equate it to cosine squared of x, so that we can find the values for a, b, and c. So getting the first derivative of our yp prime is just equal to the derivative of a constant is 0. The derivative of this, now remember that the derivative of cosine of u is just equal to the derivative of cosine u, which is the negative sine of u, times the derivative of u. So for this case, the derivative of our u is just equals to 2. So I am going to write negative 2b sine of 2x, and the derivative of sine is a positive cosine, so plus 2c cosine of 2x. Now getting the second derivative, still using the same process of differentiation, so I will have negative 4b cosine of 2x minus 4c sine of 2x. Now after getting this one, I am going to substitute this to here, so I will have, you can see y double prime, so I have negative 4b cosine of 2x minus 4c sine of 2x times 2 times our y prime of p, so I have negative 4b sine of 2x plus 4c cosine of 2x plus our yp, which is plus a plus b cosine of 2x plus c sine of 2x, and we are going to equate this with 1/2 plus 1/2 cosine of 2x. There. Now simplifying this term here, we can combine this one with this. So I will have negative 3b cosine of 2x, and another one is here, plus 4c cosine of 2x, and another one should be this one and this, so minus 3c sine of 2x, and this minus 4b sine of 2x plus a, don't forget that, this is equals to 1/2 plus 1/2 cosine of 2x. Now factoring cosine of 2x here, so I have cosine of 2x times 4c minus 3b, and also factoring sine of x plus sine of x times negative 3c minus 4b plus a, and this is equal to 1/2 plus 1/2 cosine of 2x plus 0 sine of 2x. I'm just writing 0 sine of 2x because the next thing we're going to do is we are going to equate same coefficients. So here, cosine of 2x, cosine of 2x, we are going, since they are the same, cosine 2x, so we are going to equate their coefficients. So this will be 4c minus 3b equal to, coefficient of our cosine 2x here is 1/2. The other one, our sine of x, negative 3c minus 4b is equal to 0, and the value for our a here is this, a constant. A is a constant, so it's just this. So we have a equal to 1/2. So that is the value of our a. So the next thing we're going to do, we're going to solve for the values of c and b. So from here, we have c is just equal to negative 4/3 b. And substituting this here, I have negative 16c over 3 minus 3b, and this is equal to 1/2. So I have b equal to negative 3 over 50. Do the math. And for our c, the value of our c here is just negative 4 over 3 times negative 3 over 50. So I have 2 over 25. Thus, our particular solution, so we go back to the form of our particular solution, which is this one. So our yp is just equal to a. So the value, remember that the value of our a is 1/2 plus the value of our b is, remember that it was negative 3 over 50 cosine of 2x, and the value of our c was 2 over 25, so plus 2 over 25 sine of 2x. So thus the complete solution for this differential equation, which is y equal to yc plus yp, is just equal to our homogeneous part, which was c1e to the negative x plus c2x e to the negative x plus our yp plus 1/2 minus 3/50 cosine of 2x plus 2/25 sine of 2x. So this is our general solution, or our complete solution for this differential equation. Okay, now to prove that y is just this one is a solution of this differential equation, y prime plus r1 r2 y equal to a e r1x, we're going to use the variation of parameters. Now, to solve using variation of parameters, we still need to solve for the homogeneous part. So the homogeneous where this is equal to 0. Now, just like in the previous item, rewriting this one, I have m squared minus r1 plus r2 m plus r1 r2 equal to 0. Now, here, we cannot solve the value for m merely by factoring. So we are going to use our quadratic formula. We call that our quadratic formula. For example, we have m, this is just equal to negative b plus minus square root of b squared minus 4ac over 2a, where abc is coefficients of this a, x squared plus bx plus c equal to 0. So for this case, m here is just equal to the negative of b. Our negative b is negative r1 plus r2. So negative times negative positive. So I have r1 plus r2 plus minus square root of our b squared. So I am no longer going to write the negative here, since squared it will just be positive. So I have r1 plus r2 squared minus 4 times our a here is just 1, so times c, which is r1 r2, so 4 r1 r2 over 2 times a, which is just 1, so 2. Simplifying this portion here, I'll have r1 squared plus 2r1 r2 plus r2 squared minus 4r1 r2. So the term here can be simplified as r1 minus r1 squared minus 2r1 r2 plus r2 squared, and this can be factored as r1 minus r2 squared. So this, the square root of that is just actually equal to r1 minus r2. So rewriting this expression here, I'll have m is now just equal to, okay, so that you can see this, r1 plus r2 plus minus this, since the square root of this is just equal to r1 minus r2, so plus minus r1 minus r2. Don't forget the parenthesis sign here, parenthesis, because we have a negative here. So and this will be all over 2. So we have two values for m here. m1 is when r1 plus r2 will be added to r1 minus r2 and over 2. So r2 will cancel here. I am left with 2r1 over 2. So thus m1 is just equal to r1. Now for the case of our m2, m2 is when we take the negative 1. So r1 plus r2 minus the quantity r1 minus r2 over 2. So this will be r1 plus r2 distributing the negative sign, minus r1 plus r2 over 2, canceling r1, I am left with 2r2 over 2, canceling that, now I am only left with r2. Thus, notice that we took the assumption that r1 is not equal to r2. Now remember that if our m1 is equal to our m2, we have the form y equal to c1 e to the m1x plus c2x e to the m2x. Now, since we took the assumption that they are not equal, so we took the case where the form of our solution is y equal to c1 e to the m1x plus c2e to the m2x. So the solution for our homogeneous portions is yc equal to c1e, where our m1 is r1, so r1x plus c2e to the r2x. And this is the solution for a homogeneous part. Now, for the variation of parameters, we will get our y1 and y2 from here. This one will be y1 and this one will be y2. So here, rather than saying it in another way, the values of our y1 and y2 will always be derived, or we will always get it from the general solution of our homogeneous equation. So thus, we have to solve for the homogeneous equation first in order to get y1 and y2. So for this case, our y1 is equals to e to the r1x, and our y2 is just equal to e to the r2 of x. Now, next thing we're going to do is we're going to use the Wronskian in order to find the values of our u and y, because we are aiming to get the particular solution of this differential equation having the form yp equal to u1 y1 plus u2 y2, where we will be solving u1 and y2 here now. So the first thing we're going to do is to use the Wronskian method, where w is just w of our y1, y2 is just equal to y1, y1 prime, y2, y2 prime. So here, our Wronskian for e to the r1 of x and e to the r2 of x is just equal to e to the r1 of x times the derivatives of this. Remember that r1 is constant, so the derivative of this is just r1 e to the r1 of x, and we have e to the r2 of x. Derivative of this is just r2 e to the r2 of x. Now, getting the value here, I'll have r2 e to the r1 plus r2. I just factored x here, and for that case I have negative r1 e to the r1 plus r2 of x. I'm just using the matrix rule, whatever. So factoring this, I'll have e to the r1 plus r2 of x times r2 minus r1. That is my w. So my w1 is just equal to 0 times the function of x, y2 prime. Now, where can I get this function of x? Function of x is just the non-homogeneous part. Recall that this part, when our differential equation is already written in standard form. So since this is already in standard form, since this is 1 here, so our function of x here is just equals to a e to the r1x. So using this one, I have w1 is just equal to 0 a e to the r1x. Our y2 is just e to the r2x, r2 e to the r2x. So that is 0. So we have negative a e, so just add the exponents, r1 plus r2 x. So my W1 is just negative A e to the R1 plus R2 x. Now my W2 takes the form y1 prime 0 function of x. So this is just our y1 here is just e to the r1x, where y prime is r1 e to the r1x, and 0 or function of x is this a e r1 of x. So this is a e to r1x. I'm just adding r1 plus r1. This is 0, so plus 0. So now to solve for our w1, we're given that w1 prime is just equals to w1. What w1? u1 prime rather, sorry. u1 prime is just equals to w1 over w. So our from here our w1 is just equal to negative a e raised to r1 plus r2 x over our w takes the form this e to the r1 plus r2 x times r2 minus r1. So from here we can cancel this. So we are now left with negative a over r2 minus r1. Now to get u1, we are just going to integrate this. So integrating this, so don't get shock of this form. This is just a constant. So the derivative of the integral of this is just, so u1 is just equal to, since this is a constant, so that one is just equal to a over r2 over r1 times x. So for our u2 prime is just equals to w2 over w, where our w2 is this is equals to a, there, so you can see our w2 is just a e to the 2 r1x over our w, which is just equal to e to the r1 plus r2 x times r2 minus r1, there. So for this case, I can't cancel this one directly, but I can rewrite this as e to the r1x times e to the r2x, so such that I can cancel this and that ones. So I am left with a e, so take note, I am going to move this one upwards, so this will be e to the negative 2r, and add it with that. So I have e r1 minus r2 x over r2 minus r1. Now this seems not really a bit tricky, but maybe sometimes hard to look at. That to find the integral for this, you are just going to let u, or rather let w, be equal to r1 minus r2. So our dw, this is dx if you're going to get the integral for that one. So our dw is just equal to, r1 minus r2x, since we aim to express this as e to the w, since the integral of e to the w is just equals to e to the w. So the derivative of this in terms of x is just r1 minus r2 dx. So my dx is just equal to dw over r1 minus r2. So thus I can rewrite this, since this one and this is constant, so I will just put it out the integrand sign. So I'll have a over, and this one, by the way, I can rewrite this as negative r1 minus r2, so that I can combine it with that one. So I will have negative r1 minus r2 squared integral of e to the w dw. So just notice that this part I just took it out from the integral sign, so this one becomes squared. So from here, our integral for that one is negative a over r1 minus r2 squared times e to the w, where my w is just equal to r1 minus r2 x. So that is my value for my u2. Now, so my particular solution y is now just equal to yp is takes the form u1 y1 plus u2 y2. So my u1 was my u1 from here is just negative a over r2 minus r1x. My u2 was negative a over r1 minus r2 squared times e to the r1 minus r2x, where my y1 is just equal to, wait, my y1 was here. My y1 is just equal to e to the r1x, and my y2 is e to the r2x. So substituting it here, so I have negative a over r2 minus r1 times my x times my y1, which is e r1x, plus my u2, which is just equals to the negative a over r1 minus r2 squared times e to the r1 minus r2 x times my y2, which is e to the r2 x. So my r2x here will just cancel, so I am now just left with my yp is now takes the form a over r2 minus r1 x e to the r1 x minus a over r1 minus r2 squared times e raised to r1 x. So my complete solution for this differential equation is just y equal to c1 e to the r1x plus c2 e to the r2x. This is my homogeneous part. Recall that our general solution is composed of yc plus yp. So plus my yp, which is just negative a over r2 minus r1x e to the r1x minus a over r1 minus r2 squared times e to the r1x. And the problem states that we have to prove, or we have to show, that y equal to ax e to the r1x is one of the solution of our of this differential equation, where our a can always be determined if our r1 is not equal to r2. So take note that this general solution is composed of independent solutions. Now when I say independent, or rather they are linearly independent solutions, they are just not a constant multiple of one another. So each one of this is a solution of our differential equation. Now I would like you to take a look at particularly at this one. This is one of the solutions of our differential equation, and this portion here is a constant. Now I can just rewrite this portion here, including the negative sign, as a. So I will let a, capital A, equal to negative a over r2 minus r1. So this part here, I can rewrite this as a x e to the r1x, and so this means that this is one of the solution of our solution of our differential equation. Now take note that if r2 is equals to r1, so a constant will be divided by 0 and it will not be determined, it will be indeterminate. So our assumption was correct, that r1 must not be equal to r2, so that we can determine the value of a always.